Metals are used in many everyday objects.
Kind of loud.
This morning, when I woke up, I decided to have a soft-boiled egg and a cup of coffee. The pot I used is made of metal. The kettle is made of plastic, but the coiled heating element inside it is made of metal. Metals are good conductors of heat. This is the reason why metals are used to make these everyday objects. You would never see a pot made of wood or a heating element made of plastic. Metals are also good conductors of electricity. The wire connecting your kettle to the electrical socket is actually made of many copper wires, insulated with a layer of rubber. Think about the shapes of the everyday objects we described. The pot, the heating element inside the kettle, and the copper wires. Notice that they are very different. Metals are malleable. This means that they can be molded into different shapes. Metals are very ductile. This means that they can be stretched into wires. To fully understand these properties of metals, we must understand metallic bonding. When we talk about metallic bonding, we are actually describing the electrostatic attraction between the metal ions arranged in a lattice structure and the free-floating electrons around them. Since these electrons are free to move around, the term sea of electrons is also used. What is a lattice structure, and where have you heard this term before? Let's pause the lesson to think about this and resume when you are done.
Pause now.
The term lattice structure means that there is a regular repeating pattern. We have heard this term before when discussing ionic lattices. It is used to describe the alternating positions of the metal and nonmetal ions. In metallic structures, however, there are only metal ions. These metal ions are arranged side by side in a regular repeating pattern. The free-floating electrons act like a glue and hold the structure in place. This is a very strong attraction and explains why metals have high melting and boiling points. A lot of heat energy is needed to overcome this attraction. This is also why metals are very good conductors of heat. Free-floating electrons are the reason why metals can conduct electricity. Metals are malleable and ductile because no matter what shape the metal takes, the free-floating electrons will conform to that shape. The strong electrostatic attraction will remain, and therefore the structure stays intact. Let's think about it. Cars and bicycles, trains, planes, buildings, cutlery, spectacles, furniture, and endless items can be made from metals. To recap, the electrostatic attraction between metal ions arranged in a lattice structure and free-floating electrons is known as metallic bonding. This explains many properties of metals. They are good conductors of heat and electricity, have high melting and boiling points, and are malleable and ductile. Free-floating electrons is known as metallic bonding.
Okay, I need you to draw that in your notes. Something that looks like that. These are your cations, positive metal ions. Pick any metal on the periodic table: copper, iron, sodium, strontium, francium, whatever. Individual metals have metallic bonding. There's no such thing as two metals bonding together. We're going to learn about alloys real brief, okay? If I have time today, I'll talk about it. I should have time, actually. So alloys are not chemically bonded. It's different, so I'll talk about it. So when I say, or when you read metallic bonding, what this picture is, what this image is one metal element. So each positive sign you see could be whatever metal you're imagining. Let's say copper. Let's imagine, we're all imagine copper, so we're on the same page. Each one of these would be a Cu+2 or a Cu+1, depending on the charge it uses, but it's copper with a positive charge. Copper's valence electrons are these negative charges that are free-flowing. They call it the sea of electrons. So I want you to draw this because this is what it looks like. If you were to like zoom in with a really strong microscope and be able to look at how a metal is arranged, these positive ions, those are the metal atoms basically, those would be staggered, right? So they don't line up perfectly, they'd be staggered a little bit, and then the negative electrons would be constantly moving around them. I use the analogy of like boats that are anchored or in a marina or on a dock. Boats that aren't moving, the boats are the positive, and then the water would be the electrons, right? So if you just imagine a whole bunch of boats in like some sort of bay somewhere and they're all anchored or they're not moving, they're just kind of floating there. That's kind of what the metal ions here are doing. They're basically just stationary, all right? And then the water, the electrons, is flowing in and around it, okay? So that's exactly what metallic bonding is. I asked you to write that down, all right? But I'm kind of going over that anyway. So that's an important concept because ionic, so eyes up here, ionic would be positive, negative, positive, negative. They wouldn't have these electrons flowing. That's the difference. They both use positive, negative attraction called electrostatic, but metallic, there's no negative ions. It's just positive ions with its own electrons. All right, another analogy to make sure you really get it. If I was to flood this room with 2 feet of water, you guys would be the metal ions and the water would be the electrons. You're just sitting here. You're not moving, okay? You're not moving, and the water would just be moving around, okay? So we want to make sure you really understand that concept. Okay, give me what I asked for. Malleable. Watson, what's that? What's malleable mean? Good, molded into different shapes. Molded in, technically, you're right, very good. That's what she said. In the book, I think it would say hammered into sheets or flattened into sheets. Technically, that's malleable. But really, malleable just means you can mold it, right? Like clay. Clay is malleable, right? Think of it that way. So metals are malleable too, but clay you can mold, or think of Play-Doh, right? You can mold it with your hands. Metal, maybe not, right? You need heat, pressure, and then you can start bending it. Blacksmiths, right? What do? Well, they heat the metal up till it, yeah, red hot, and it becomes a little more pliable, like softer. Then they hammer it, like hit it, literally hammer, hit it very hard, and it takes that much force, even when it's hot, to bend it, right? Okay, what was the other one? Ductile.
Can we stretch out into wire?
Yep, formed into wire, stretched out into wire, good. All right, there was like 3 other properties, so you needed at least one more. Morgan. Conducts electricity very well, good. Conducts heat very well, good. There's one more thing. Trevor. High melting and boiling points, right. So I'm not writing this down. Okay, you're big boys and girls. You can write all this stuff down as I'm saying it. So make sure you have those things. Ready? Malleable, ductile, you should already have it. Conduct heat and electricity. You already know all of this. That's why I'm kind of a little looser than usual. I'm not writing everything down here. We already learned about metals in the beginning of the year. So conducts heat, conducts electricity, ductile, malleable, high melting, high boiling points. Why? Strong attraction. Positive, negative is very strong. Now, because the electrons can move freely, the sea of electrons, if you were to hit this metal, these positive ions can actually just glide on top, we'll say on top of the electrons. Okay, again, boats in water. I use the analogy, it's a good one. If you push the boat hard enough, it will move on the water. Same thing. You hit these hard enough, that's why it can bend. It doesn't break because they move. Whereas if it's ionic, when you have the positive, negative, and you hit them, they break. There's none of this mobile stuff, right? So that's different. When you run electricity through metals, what ends up happening is these mobile electrons start moving with the current. So if we put the electricity on this side of the metal, it'll flow this way and then come out this side. So that's like negative, positive of the battery, right? So the electricity will move, and those mobile electrons, those sea of electrons, they'll go with the electricity. So that's why it conducts, because of the mobile electrons. So that's basically all you need to know about metallic bonding, okay? So I'll probably just give you a couple examples, but really all it is metal elements. So copper by itself, zinc by itself, calcium by itself has metallic bonding, okay? What else do you need to know? They're strong, okay? Ionics are strong, metallics strong, covalents are weak. We learned that in lab. All right, so these are also strong. You know metals are strong. Okay, you know that already. Questions about any of this? Okay, lights please. So just some examples here. So examples of metallic bonding: solid Cu, solid Fe. And remember, we could put CuS, FeS, that means solid. Those are just, giving you examples seems so silly. It's just pieces of metal. Solid potassium, solid K. Any metal element has metallic bonding. That's it. Some of you double check my notes. Sometimes I do everything off the top of my head and I forget some things once in a while. See if there's anything else I want to talk about here with metallic. That's it. What do you call, just real quick? So you have your positive cations here. I'm trying to stagger these a little bit. And then you have your negative valence electrons that are moving around. What do you call that attraction? What holds this together? There's a word, starts with an E.
Electrostatic.
Electrostatic. Okay, I'd like you to remember that. Electrostatic. We had it up there on the board. I forgot I was going to have you look those up. Electrostatic is between negative and positive. That's an important word. Any of you who are sophomores, if you want to take AP Chem when you're seniors, because I don't teach it next year, that's an important word, electrostatic. Do I expect you to remember it for 2 years? Maybe not, but at least if you take AP and I bring it up, you're like, okay, I remember hearing that. So, anyways, ionic, again, I want to make this real clear. So I know I'm repeating myself a lot, but actually we had a faculty staff day last Friday, remember, because you guys didn't have school. So we had an assembly, whatever, a meeting in the auditorium with like everybody, and Dr. Mundell was talking about stuff, and he said, I think he said it takes 21 times that someone hears something that they will remember it. 21 times.
He's a smart guy.
So if I've said electrostatic, I've probably said that maybe 10, 15 times. So I'll just keep saying it, electrostatic, electrostatic, electrostatic. There we go. So that's 3 more. So anyways, I just thought that was interesting. That's the way it is with lots of things, right? Repetition helps you get better at anything. But anyways, thought that was interesting. There's electrostatic here. There's another one. And electrostatic here. We're almost at 21. The difference, this is ionic. This is metallic. So I know sometimes the video and I'm talking a lot and you're not talking, I'm not calling on people, so you zone out. So stay with me right now and I want someone to answer this. What's the difference between these two pictures? They both have the same force of attraction. This is ionic, this is metallic, both really strong, high melting points, but what's the difference? Mike?
The electrons are free flowing.
In? Which one are they not free flowing?
Oh, in the bottom one.
Right. Very good. There's no free flowing electrons here. Good job, Mike. One more difference. In fact, it's kind of along the same lines. In this drawing, I don't even have any what? There's no electrons here at all. That, what's a positive atom called? Cation. What's a negative atom called? Right. Saying positive atom and negative atom is kind of incorrect. I shouldn't even be wording it that way. What should I be calling them? An atom with a positive charge is called a cation. Right. Ion. Right. I shouldn't be calling them atoms at all. That's a positive atom. Fail. Positive ion, negative ion. So these would be like Na plus, Cl minus. Here, this would be just Na. This would be a piece of sodium, and these would be Na plus with the negative valence electrons. So I feel like I'm saying the same thing over and over and over. I really hope you understand the difference. You hit this with a hammer, it breaks. There's nothing moving. There's nothing to cushion it. Here, you got that sea of electron to cushion. All right. I think I beat that to death, so we're done with that. All right. Real quick, what is an alloy? Real quick, what is it? It is a mixture, and I'm going to put in parentheses here, it's physical. a physical mixture. There's no bonding going on at all. All right? A physical mixture of two or more atoms. You know what? I didn't word that very well. Bless you. I should say two or more different atoms. So I'm going to squeeze that in there. Different atoms. So, for example, the most common alloy is steel. That anyone thinks of or knows, and maybe you didn't know it was an alloy, but it is. The two atoms used are iron and carbon. And then there's stainless steel. You have to add something else in there too. There's different kinds, but you can add some chromium in there as well. Someone give me another alloy. I have some examples here. Think of another alloy. The two that are most common that students usually, somebody says, is they both start with a B. Think of the Olympics.
Brass.
Bronze. Well, bronze is where I was going, but brass is another one, right? So bronze. Oops. Bronze is another example of an alloy. Brass. What's brass? It looks gold, right? It looks like it's gold, but it isn't. So bronze, I always forget the percentages here. Bronze is, well, it's copper and tin. Mostly copper, Cu and Sn. But apparently there could be some zinc, lead, and phosphorus in there as well. So it's actually a big mixture. Those are the two biggest percentages. Somewhere between, I wrote between 50 and 98%. Then I wrote between 0 and 35. So you don't need to know the details. But again, bronze, copper, and tin. And then brass was copper and zinc. Copper and zinc is brass. So there's two different types. These two are the two different types of alloys. All right. One is called interstitial. That's this one. And one's called substitutional. That's this one. You don't need to know that. Okay. But the difference here is iron is really big. So you can just watch this. This is pretty interesting. I think it's interesting. So you got iron, which are pretty big. They're all supposed to be the same size. Okay. So those are all Fe. Now carbon is tiny. Look at Fe. Fe has 26 protons, 26 electrons. Hey.
Signature.
Yeah, I came down earlier, and you weren't there, and then I didn't make it back.
I'm trying to fill the squares in today.
Yeah, no, I got you.
Yep, just print and sign.
Print
Yep,
here.
Sorry about that.
Oh, no, that's all right. Okay.
Perfect. Thanks.
Thank you. All right, so if you look at iron, 26 protons, 26 electrons, and then carbon, 6 protons, 6 electrons. Carbon's really tiny, iron's pretty big. So carbon actually squeezes in these spaces, right? So imagine if we filled this whole floor with basketballs. Okay, so all the floor was covered in basketballs, so all the basketballs were touching. There would be these little diamond-shaped spaces in between the balls. Does that make sense to you guys, hopefully? All right, without actually doing it. So those spaces are filled with carbon. That makes this lattice structure really strong. So steel is stronger than iron because carbon comes in here and fills these spaces. That's called interstitial. That space right here is called the interstitial space. So carbon fills that up. And then brass is a different type because what happens is brass, let's say this is our Cu. Let's say the blue one is our zinc. And it kind of alternates. Okay, Cu, Zn. Sorry, this is tricky here. Zn. So instead of filling in spaces, it's just atoms substituted. So I take copper, put a zinc, take a zinc, put a copper. So they kind of, it's not exactly alternating, but that's this type of alloy. These are usually stronger because they fill the spaces. These are usually not as strong. But the reason our society uses alloys is they're stronger. They're usually stronger, sometimes lighter too. All right, do those practice quizzes, and we'll have that quiz on Monday. I hope we are here.